In this video, we'll take a look at section 3.4, graphs of polynomial functions. So let's review some of the functions you're familiar with and then take a look at a couple of common functions. So you've looked at linear functions already. Possible graphs could have a positive or a negative slope. The degree is 1. There are no turning points. And then in behavior, if you have a positive leading coefficient and a negative coefficient, and the degree is odd. So remember, linear is in the form mx plus b. Quadratic you've worked with, that's a function of the form ax squared plus bx plus c. So if your quadratic function has a positive leading coefficient, it opens up. Negative, it opens down. The degree is 2. It has one turning point, one less than the degree. And in behavior, if you have a positive leading coefficient and if you have a negative, and it's even. So as you get higher degree polynomials, your choices for what the graphs look like increase. So a cubic that has an x cubed plus bx squared plus cx plus d, we're adding in more coefficients and more terms. It could look like just an increasing function like x cubed, or it could have 2 turning points. So the degree is 3. It could have 2 turning points or none. And then we've got in behavior for both positive and negative leading coefficients. If you have a quartic, that's a 4th degree polynomial. It could look like a lot like x squared. It could look a little bit like an x cubed right here and then move back up, or it could look like a w. And it has degree 4. It might have 3 or 1 turning points, and then we've got in behavior. So as we just want you to be able to look at a function and have a good idea of what it looks like. And that's what the goal of this section is. So let's take a look at a function f of x. It's already in factored form, equals x plus 3 times x minus 2 squared times x plus 1 cubed. So the degree of that polynomial, add together the degree of each factor. X plus 3 is to the factor of 1, plus x minus 2 is to the factor of 2. X plus 1 is to the power of 3. So we have a degree of 6. So I know this is even degree. Lead coefficient is positive if I were to multiply it out. So the in behavior is pointing up. The zeros, as we take a look, or x-intercepts, if you set each of these factors equal to 0, x plus 3 equals 0, you get negative 3 is a 0. X minus 2, set it equal to 0, you get x equals 2. And then x plus 1, set that equal to 0, you get an answer of negative 1. So the zeros and x-intercepts, zeros are at negative 3, 2, and negative 1. The intercepts themselves are negative 3, 0, 2, 0, and negative 1, 0. So what happens at each x-intercept actually depends on the power, and it's called a multiplicity. So notice at x plus 3 at negative 3, the function goes through the x-axis. It goes right through. That's linear, and it kind of looks linear as it goes through. X minus 2 is squared. At the x-intercept 2, notice your graph looks a little bit like x squared right there. It touches the x-axis and goes back up. At x plus 1 cubed, at negative 1, notice your graph looks kind of like x cubed right there. It goes through the x-axis. So to summarize what that means, what happens at each x-intercept, the graph is either going to touch or cross the x-axis, and it depends on whether your degree is odd or even. So if a polynomial contains a factor of the form x minus h to the power of p, the behavior near the x-intercept is determined by that power p. We say that x equals h, it has a 0 of multiplicity p. So in this case, the value 2 has a multiplicity of 2 because the power degree is 2. At negative 1, it has a multiplicity of 3. So the graph will touch the x-axis at zeros with even multiplicities, and it will cross the x-axis at zeros with odd multiplicities. And the sum of the multiplicities is the degree of the polynomial function. So it's possible to have a multiplicity of 1. We have x plus 3 to the power of 1, so negative 3 has a multiplicity of 1. So now putting all this together, how do you sketch a graph of a polynomial function? Find your intercepts, x and y. We know how to do that now. Check for symmetry. See if your function is even or odd. That gives you some information. Use the multiplicities of the zeros to determine behavior at the x-intercepts, whether it crosses or whether it touches. Determine end behavior. Use end behavior and the behavior at the intercepts to sketch a graph. We won't be able to find exactly where the turning points are, but you can get a pretty good idea of what the graph looks like. And then we want to make sure the number of turning points is not more than 1 less the degree of the polynomial. And then we can use technology to check. So we're going to take a look at a multiple choice. Pick the graph of the following function. So our f of x is x squared times x minus 3. So the x-intercepts are at x squared equals 0. So at x equals 0, with multiplicity of 2, that means our graph is going to touch the x-axis at 0. Okay, so 0, 0 is an x-intercept, and our graph is going to touch there. Then we have x minus 3 is equal to 0. X is equal to 3. This has multiplicity of 1. It's odd, so it's going to cross the x-axis at the point 3, 0. Okay, so 0, 0, and 3, 0. So let's take a look at our multiple choice. The first one is not a possibility because it touches at negative 3. The second one is not. So we either have the third option or the option down below. Okay? Our leading coefficient is positive, so that doesn't narrow anything down. It's the multiplicities. So a multiplicity of 2 means it has to touch at 0, 0. The third graph crosses at 0, 0, so it must be the graph down below. So it increases, touches, goes back down, comes back up, and crosses at x equals 3. All right, another theorem, something called the intermediate value theorem. This just lets you know, let f be a polynomial function. The intermediate value theorem says that f of a and f of b, if they have opposite signs, then there exists at least one value c between a and b, which f of c equals 0. This kind of narrows down your zeros. For example, look at our graph. F of 2 in the graph above, f of 2 is equal to negative 4, and then f of 4 is, I don't know what it is, I'll guess, 10. If your graph, if f of 2 is negative and f of 4 is positive, that means somewhere in between 2 and 4, there has to be a 0. And if you look at our graph, 3 is at 0. So you might have questions to show a function, this particular function, this polynomial, has at least 2 real zeros between x equals 1 and x equals 4. What that means is to make a table of values and evaluate f at 1, 2, 3, and 4. So if you open up Desmos, or I'll just use the graphing calculator. Let me get the graphing calculator up. That would probably be quicker on this case. So type in your y equals the function itself. We have x to the third then minus 5x squared plus 3x plus 6. And I'm going to have the calculator do a table of values for me. So if you haven't used this before, you can go table let's see, I want to put the values in myself. I have them here. F of 1 is 5. You can set the table, there's a table set where you can set it to ask for the independent variable. That way when you go to the table, you can put the values in, only the values that you want. So I want to put in a 1, a 2, a 3, and a 4. So the values that come out are 5, 0, -3, and 2. So there has to be at least 2 zeros because I go from 2 to 3 goes from positive to negative, and 3 to 4 goes from negative to positive. So you're taking a look and seeing whether your signs switch. That tells you that your graph has to cross the x-axis at some point to get to those y values. All right, next example. We're going to write a formula for the function that's shown using what we know about polynomials. So I know that I have x-intercepts at -1, at 2, and at 4. So I know that since I have an x-intercept at x equals -1, 2, and 4, then the factors are x plus 1, x minus 2, and x minus 4. So I know that I'm going to at least multiply these three together. Then I want to figure out what the multiplicities are at each of these zeros. And that's what does the graph look like. So at the -1, the graph touches and goes back down. So that has to be even. So the smallest even is squared. So I know that x plus 1 squared has a multiplicity of 2. At 2, notice the graph crosses, but it also looks like x cubed as it crosses. So x minus 2 has a multiplicity of 3. At x equals 4, the graph goes straight through. It looks linear, so that's a multiplicity of 1. So what I don't know, though, is I don't know what I'm multiplying my function by. So the function is going to be something a times the x plus 1 squared, x minus 2 cubed, x minus 4 to the power of 1. So what you do is take a look at your function and select a point on the function. So I'm going to select the point -4, 0, -4. I know that the point 0, -4 is on my function. So I'm going to substitute 4 for my y coordinate, 0 for my x coordinate, and then I'm going to solve that for a. So I get 4 is equal to a times 1 times -2 cubed, which is -8, times -4 to the power of 1, which is -4. I get 4 is equal to positive 32a. Divide both sides by 32. I end up with 1/8 is equal to a. And then I know that this is in behavior, has to be a negative coefficient in the front. So a has to be a -1/8. So that's how you find, you use in behavior and use your intercepts. And then to find a, substitute a value for x and y. Well, that should have come out, that's 0, -4 here. Let me change this real quick. That means it should have come out -1/8 anyway. I just didn't put it the -4. All right, last example, a polynomial inequality. If I want to solve a polynomial inequality, first rewrite your function so that all values are on one side and 0 on the other. So I'm going to take m to the third to the other side, and then I'm going to rewrite it, m to the third plus 5m squared minus 84m, and I want to make sure my inequality points the right direction. If I take the m to the third over, I'm going to have less than or equal to 0. So I want to solve the inequality m to the third plus 5m squared minus 84m less than or equal to 0. Why did I put it that direction? I want to deal with a positive m to the third. Okay? So before we deal with the inequality, replace the inequality with an equal sign and solve the polynomial by factoring. So I'm going to factor out an m. I'm left with m squared plus 5m minus 84 is equal to 0. Continue factoring two numbers so that when we multiply them, we get negative 84 and add and get 5. 84 is 12 times 7. That needs to be a positive 12 and a minus 7. So I have three intercepts, or three zeros. M equals 0, m equals 7, and m equals negative 12. So that basically cuts my number line, 0, 7, negative 12, into three pieces. I know that my polynomial is equal to 0 at each of these places. And what I want to do is I want to test values in between these values. These are called critical values where it equals 0, to see if they're positive or negative in the function. So what I would do is I would take a value between 0 and negative 12, maybe negative 1, and put it in the function and see what the output is. I just want to know if it's positive or negative. Then I would take a value between 0 and 7 and put it in the function and see, I just want to know whether it's positive or negative. So if I put a negative 1 in, negative 1 cubed plus 5 times negative 1 squared minus 84 times negative 1, I'm going to get a negative 1 plus 5 plus 84, which is positive. So that means for all the values between negative 12 and 0, I'm going to get greater than or equal to 0. Then test a value, test a 1. I get 1 cubed plus 5 times 1 minus 84 times 1. That gives me 1 plus 5 minus 84. That's going to be negative. That tells me that all the values between 0 and 7 are going to be negative. And then if I test a value on to the right of 7, I'll get positive. So what does this mean? If you graph the function, notice our zeros are at negative 12, 0, and 7. Our function is increasing and above the x-axis, then it's below the x-axis, then it's above. So on the inequalities, if you're trying to solve m to the third plus 5m squared minus 84m less than or equal to 0, it's all the places where your function is below the x-axis, or where you end up with a negative with a test point. If I would have put negative 13 in, I'd get a negative value. So the answer is all the values from negative infinity to negative 12, including negative 12 because I have less than or equal to, it equals 0 at 12, along with the other place I'm below the x-axis are all the values from 0 to 7, including 0 and 7, because I want to know where it's also equal to 0.